All right, I've spent well over an hour already developing this, so hopefully this works out well. This is the example problem. We're very close to the one I gave you in class on October 24th of 2012. Now, it's already 10:28, so it'll be yesterday or a couple of days ago or last year, whenever you finally watch this. But anyway, here's the problem. We want to find all these things given this data, and we want to use these steps. Now, these steps aren't perfect, but they're pretty helpful. So I've already written step 1 and 2. I've actually written every single step already, so we can go through this quick. If you get lost on something, pause it and replay it multiple times. Or rewind it, I should say. Okay, so step 1 says write and balance the chemical reaction. So I did it. You can see it clearly right there. You've got to be able to write and balance a chemical equation. Step 2 says to write the net ionic equation, identifying spectator ions. I eliminated the spectator ions, but it would be K and NO3 would be our spectator ions. And we're going to care a lot later about these. We're going to care about what the precipitate is. We're going to care about the parts that make it. And we're going to care about the parts that don't. We're going to care about every part of what's happening in this solution. Okay, because remember, I'm putting these two solids, well, they're already in solution, so I'm adding these two liquids together. All right, next page. Step 3 says to convert molarity and volume to moles of reactants. So I set up a very simple picket fence where I solve for moles of my reactants. The problem gives me volume and molarity. Remember that volume is the loner and molarity is your proportion. You always start the picket fence with your loner and then you put the proportion next. All right, the reason why I even convert these to moles is so I can determine what the limiting reactant is. So that's going to be step 4. All right, step 4. This is kind of ugly. Let me move this over for a minute. Step 4 says determine the limiting reactant. So here we go. We solved previously, in the previous slide, for the amount of moles of both of these reactants. Now all we need to do is take the balanced chemical equation, and I just stole this from step 1. I hope that that's okay. I owned it, I made it, so I can steal whatever I want. All right, in step 1, we had this balanced equation. If you understand what a balanced equation is really telling you, then this one's very easy to figure out which is the limiting reactant. If you look up here, you have 1 lead nitrate reacting for every 2 potassium hydroxides. So another way to say that is you need twice the amount of KOH than PbNO3 2. So in order for this reaction to go to completion, meaning all reactants are consumed, I need the exact molar ratios of 2 KOH to 1 Pb. So once I have these in moles, I just have to say, all right, I have to ask myself this question. Do I have twice the amount of KOH? Is this number here twice as big as that number there? This answer is clearly no, it is not. If the answer is no, then KOH is your limiting reactant. If the answer were yes, then PbNO3 would be your limiting reactant. So we now can say that we've determined the limiting reactant. The limiting reactant is KOH. That becomes important as we move on. So step 5 has a bajillion parts. I've broken it roughly into 4 parts called A, B, C, and D. Step A is by far the most simple. It says first determine the new total volume. This will be the denominator in all the following steps. Remember that we're finding molarity. All right, that's the concentration. So the concentration I'm using is molarity. And remember that molarity is moles divided by liters. So when I add these two things together, they make a new volume in liters that I'm going to divide by. Sorry, got distracted there. All right, so as long as I can find the moles of everything now, I'm going to be set because the new total volume is easy. I take my lead nitrate volume and I add it to my potassium hydroxide volume and I get my new volume here. Step 5B isn't super hard as long as you just can kind of reason through this, and I've typed it out so I hope it makes sense, and you can also pause and read it if you need. And I've also drawn in this picture over here, come on, in this picture, it's my beaker with my precipitate at the bottom and my ions that are going to be floating around. All right, so B, it says, in this problem, hydroxide is in both the limiting reactant and the precipitate. Since all of it is used up, which is the definition of the limiting reactant, and it is removed from the solution because it is no longer soluble, which is the definition of a precipitate, then the concentration at the end would be 0. So we already can say that the concentration of at least one of these things is known to me, and that would be that the concentration of OH minus at the end of this reaction would be 0 because it is completely consumed because it's the limiting reactant, and it is taken out of solution and precipitated because it's the precipitate. That was redundant. All right. Step 5C says, all right, well, we need to find the concentration of spectator ions. The moles of spectator ions do not change in the reaction. That's why they're called spectators. What we mean by the moles is that the initial moles don't react with something else that removes them from the solution. So they just stay in solution. All right, to find their ending concentration, you take the initial moles from step 3 and divide it by the new total volume. And I have to be careful here, and this star will take you there in a second. But when you take the initial moles from step 3, in step 3 we found the initial moles of the compound. That does not always equal the moles of the ion. You have to account for the subscripts. So with KOH, which K came from, it was easy. We found it was 0.09. For every 1 KOH, I have 1 K plus and 1 OH minus. So it would make sense that if this is 0.9, then this is 0.9 and this is 0.9. All right, then here's my new volume and I get my answer. So there's another thing I would put in my ending box, that my concentration of K plus is 1.06. Now NO3 is a little bit more tricky. So let's go here. So why are the moles of NO3 not 0.07? And that's because when you found the moles early on, you found it of lead 2 nitrate. But for every 1 lead 2 nitrate, there are 2 nitrate polyatomic ions. So the moles of PbNO3 do equal 0.07, but the moles of NO3 minus are equal to 2 times the moles of PbNO3, and so the value is 0.140. So we take that 0.140, put it in this expression, and we get the answer is 1.6. So there's another concentration of NO3 it is 1.6, or another concentration to answer. All right, then step D is generally the most difficult. It's not too bad. It looks like the way I've drawn it is probably way confusing now that I look at it. But in part D, we're finding the trickiest one of all. So let's read this box first. All right. What we're doing is we're finding the concentration of the ion that's in excess that was also in the precipitate. So here we go. The excess ion is the ion in the precipitate and not in the limiting reactant. In this case, we're talking about Pb plus 2. All right, so what we're going to do is we're going to follow step D specifically, and it says that to find the concentration, I know this is super small, but hopefully your computer can read it. Well, you can read it on your computer. To find the concentration, you need to solve the following equation, and it's simply X divided by the total volume. The total volume is a piece of cake. But X, then, it says, is equal to the initial moles of excess reactant. That's what I have right here. Minus the moles used, which will be this number right here. And please read this red right here at the bottom. It says, used moles of Pb2 is equal to half the initial moles of OH minus, due to there being 2 OHs used to every 1 Pb plus 2. Then it said to look at the formula, and that's a reminder for me to write the formula. So here we go, Pb OH 2 solid. Okay, since OH is limiting, it determines, the amount of it to start with determines how much of this is being used. I will use twice the amount of OH as Pb, so the amount of Pb used must be half the amount of OH that I started with. Okay, if you need to pause or rewind and replay, make sure you do that, because it's an important concept. All right, I take those two numbers, I get 0.025, and now I take that number, that's my X as it's pointing to up here. I now take that divided by the new volume, and I get 0.29 is my new concentration of Pb plus 2. So I'm just about done. I need one little slice more and I should be set. That little slice didn't really set up in my problems, or I should say in my steps over here. So I obviously should adjust those, but it's okay. This asks for the mass of the precipitate. That didn't present itself in my steps, but we can certainly find it. The mass of a precipitate is equal to the moles of the precipitate multiplied or times by the mass of the precipitate. Like, that is really dumb, but I meant the molar mass. I better write that. Molar, meaning the mass that you find on the periodic table. So the moles of precipitate weren't super hard. We could solve that. We've already found that number once before. I used a picket fence because that's kind of my crutch and the crutch I've taught you guys. But hopefully it makes sense as to why it's 0.05 or 0.045 moles. It's because it's a 1-to-2 ratio of my limiting, all right, to my precipitate. All right, then I simply take those moles, multiply it by the molar mass from the periodic table, and I get 10.85 grams. So I believe I've answered all of that in this 14-minute clip that took me almost 2 hours to write out and talk through. Make sure that you can do these. This is very similar to the one on the test. It's very similar to the ones we do in the homework. It's very similar to ones we'll do all year long. So please fight, battle, do all that you can to get these problems.